Okay, so let's dive into it here. So again, this chapter we're going to talk about carbohydrates. Obviously, you know, some of these terms you guys have heard on because you look at the back of a juice box or something like that and it says it contains 25 grams of carbohydrates. Well, what is that exactly does that mean, right? So now we're going to be looking at this stuff from a chemical perspective here. So what exactly is a carbohydrate? If we just pick this word apart real quick, right? Carbohydrate, carbon and water, okay? And this is a really old name. It's not like these actually contain water molecules, but the chemical formula, which is one of the first things that you can figure out back in the day technology, is all sugars follow this same formula right here. For every carbon, there are 2 hydrogens and an oxygen. Okay, so that's where that name carbohydrate comes from. All right, let's take a look. One of the things we're going to have to do is classify these sugars, right? We're going to look at a certain structure and we need to be able to classify them. So 2 different functional groups. Well, actually, let's just pick this part. Let's look at one of these real quick. All right, so here is an example of a carbohydrate. You have this carbon backbone, okay? Notice off of the vast majority of those carbons, you have, what do we call this?
Alcohol.
We have these alcohol functional groups. So each one of these carbons is decorated with an alcohol group, except for one of them is a carbonyl carbon. Okay, but this is a common sort of formula that all these sugars will follow. Right? Each of these carbons are bound to an oxygen either in the form of an alcohol, that's the normal one, or a carbonyl group. There are 2 different types of sugars. They can either be aldehydes or ketones. So this is an example of an aldehyde type sugar. You can also have a ketone type sugar where that carbonyl group, you know, it's 1 carbon in, so it's a ketone instead of an aldehyde. Notice that you still then have oxygens bound to all those other carbons. Okay, so this is a carbohydrate right here. They all sort of follow that same sort of shtick. The only difference between them is going to be which side the alcohol group is on. Okay, so if I were to erase the alcohol group from over here, now this is a hydrogen and this is an alcohol group, that's now a different type of sugar. But that's really what's going to differentiate these sugars, all right? So we're going to take this in layers. So the first thing, aldehyde and ketone type sugars, okay? One thing that we're going to, I sort of like warned everybody about this back in the day when we were first studying stereochemistry, but Fischer projections are something that are universal when talking about sugars. It's actually, you know, the #1 use of them is in designing sugars. So we'll sort of review exactly what this means in sort of stereochemistry. How do we figure out the stereochemistry of these various asymmetric centers as we're going here? All right, but step 1, first thing you need to know, be able to distinguish whether your sugar is an aldehyde or a ketone, and we'll get some fancy terminology for those here in a second. One of the things you will hear me say all the time is the word sugar instead of carbohydrate. All right, they are synonyms. Carbohydrates are sugars, sugars are carbohydrates. All right, so it's just a simplified way of saying it. When you look in your cabinet, you find a bag of sugar. That is one very specific type of sugar called sucrose. Nonetheless, if you're a biochemist, the word sugar is just synonymous with carbohydrate. You can have simple carbohydrates or simple sugars, and those will just be monosaccharides, so they will contain 1 unit that looks something like this. You can also have complex carbohydrates, which is essentially multiple units that look like this, all linked together. And that's sort of going to be the last thing that we cover are these complex carbohydrates. So let's just go. Again, we're going to take this step by step. So now we got a fancy word here. Our sugars that contain aldehydes, those are aldoses, and these ose ending is going to be something that we're going to hear over and over and over again talking about sugar. If you hear ose, it's a good indication that that particular word pertains to sugars. Okay, so aldehydes, those are aldoses. And if it contains a ketone functional group, then it is a ketosis. Okay, so these are now our two categories of monosaccharides, right, or simple sugars. Ketose and aldoses. So everybody take a second and indicate which one is which here. Where's my aldose, on the left or the right?
On the right.
This would be my aldose. And that means that this guy is my ketose. Okay, so this is sort of our level 1 for classification here. Level 2 is the number of carbons. All right, so this will follow, your simplest sugar is a triose. A tetrahose has 4 carbons, pentose has 5, hexose has 6. Okay, so this is a 1, 2, 3, 4, 5, 6. So this is a ketose, that's a hexose. Is this also 6? 1, 2, 3, 4, 5, 6, 7. The heptose, although those don't actually, we're not going to see very many of those. Okay, so let's just make sure that we all remember how these Fischer projections work. Do me a favor and classify these based on the number of carbons they have as well, right? So we already indicated here is our aldose, here is our ketose. Now we got that second level of classification. How many carbons do we have in each of these?
6.
Yep, so these are both hexoses. 1, 2, 3, 4, 5, 6, right? So remember, at each of these intersections in our Fischer projection is one of those carbons. Some of them are explicitly drawn. Those are the ones that pertain to the, what's going on here? Okay, so that's unfortunate, but my iPad decided to randomly restart itself. Technical difficulties, hold on a second. All right. I'm not sure what the hell happened there, but all right. Might be. I don't remember exactly. Bottom line, first level of classification, whether it contains the ketone or aldehyde group, and then next, based on the number of carbons. All right. Now I'm going to have to dig way, way back in our minds here. See if you can't figure out whether we have R or S stereochemistry at our blue asymmetric center here, these carbons. Everybody take a second and see if you can't remember how we go about figuring that out. Take a 10 while we do that.
It's S configuration.
Very good. For which one, left or right?
For the left one.
All right, so first of all, how do we do this? Let's remember that real quick. We got to go through and label each one of these groups around the asymmetric carbon with their priority. All right, so what's our highest priority group here?
The alcohol group.
The alcohol group is going to be the highest. That gets 1. And now we have both of the, that's because it's an oxygen, right? So that has the highest periodic number, highest number of protons. We go to the next level. I have 2 carbons here. So which one of these is going to win in terms of priorities?
The one with the hydroxy group.
No, not the one with the hydroxy group. It's going to be the one with the ketone, or the carbonyl group, right? Because this is double bonded to an oxygen. So it's as if this carbon was bound to 2 oxygens, whereas for this guy down here, it's as if it was bound to 1. So this is 3, and this is 4. Okay? Now in our perspective drawing, as long as that lowest priority group is pointed back, right, into the page, then we have going from 1 to 2, 2 to 3, and 3 back to 1. This would be clockwise. And so clockwise equals R if, as long as that lowest priority group's pointed to the back.
Why again is the aldehyde group more prioritized?
Yeah, so this, let's just like, so this guy here, because it's double bonded to this oxygen, you think of it as being bound to 2 oxygens and a hydrogen. Whereas if we had, let me get a different color. If we had this one here, we think of this carbon as being bound to 2 hydrogens and 1 oxygen.
Okay.
Right? So when there's a tie, you got to look at who's bound to what. Because it's double bonded to the oxygen, you count that twice.
Got it. Thank you.
All right. And then the other one is just going to be that mirror image. This is going to be the S configuration. Right? So perspective clockwise is R and counter clock is S, right? This is I mean, you know, honestly, it's one of those things, stereochemistry, I think I warned you guys, it was one of the hardest things when I took organic chemistry, just going back to last semester's exams. It was hard for everybody. Something to definitely just make sure you've brushed up on a little bit before we get to that final exam. Okay, but then of course the whole shtick was that when we're talking about sugars, we usually look at the Fischer projection. Okay. Now in the Fischer projection, if the lowest priority group is horizontal, all right, your lowest priority group is in this horizontal line right here, this horizontal group, which is going to be the case here. And that's, you know, the nice thing is that it's always going to be the case when we're talking about sugars. We always put hydrogen on one side and an OH group on the other side. So they're always going to be this way. Unlike sort of when we first learned about it, there were some curveballs. When that's the case, rules are reversed, right? So now clockwise is S and counterclockwise is R. So if I go through and label again, 1, 2, here's 3. Now I'm going counterclockwise, and this gives me my R stereoisomer. Likewise, this is going to be reverse. This is the S isomer. All right. And again, that's true for the Fischer projection when the lowest priority group is in that horizontal position. All right. So now this is glyceraldehyde. This is the simplest sugar that you can possibly have here, 3-carbon sugar, okay? Most of them are much larger than that. And that means that they're going to have multiple asymmetric centers. If we just sort of rewind back to the first sugar I showed you, right? Every single one of these guys is an asymmetric center. Okay, again, that's what's going to distinguish between your various sugars. They're all sort of diastereomers of one another, unless they have different number of carbons. Okay. Luckily, there's kind of like a set in stone way that we do this. Fischer projections are drawn with that carbonyl carbon at the top. Okay, and then notice this last carbon here is not sort of drawn in that Fischer projection type of way. Why would that be? Why don't I have to draw it as like C double bond O H?
Both of the hydrogens are connected to it, so it doesn't have 4 different groups. It's not an asymmetrical center.
Yeah, so it's not an asymmetric center, right? So that last carbon is always going to be sort of an achiral center. So just something to keep in mind. Okay, now we actually are going to distinguish between our sugars based on, let's just look at this carefully. We're going to label these enantiomers based on the last asymmetric center. So that bottommost carbon, if the alcohol group is on the right, we call that a D sugar. If the alcohol is on the left, it's an L sugar. Obviously, the easier one to remember is L is left. All right, so just having that simple connection in your mind helps. For glyceraldehyde, there is only that one asymmetric center. So there's only 2 possible configurations that we have for 3-carbon aldose. That is the D-glyceraldehyde or the L. Okay, so notice that we don't really use the R and the S configuration when talking about sugars. Biology, for whatever frickin' reason, has their own sort of scheme to determine stereoisomers. And again, importantly, you're only going to be looking at the last asymmetric center, right? So when we get to larger sugars, make sure you're paying attention only to that last one. All right, so this is a big ugly tree of how things are going to sort of get complicated here. We start out with our simplest sugar. This is simplest because it only contains 1, 2, 3 carbons. Okay, so that's your easiest one that you get. And then we can get more and more complex just by adding more carbons on there. Now, I'm gonna be honest with you guys. Knowing the names of these are something that you're supposed to know. I think that that's so stupid because I was able to be a biochemist for 10 years without ever knowing what the heck the frickin' sugar is because you Google it if you need to know it, all right? So I'm not gonna make us memorize this whole list of different sugars. That's just ridiculous. But yeah, FYI, if anybody asks, you know how to do it.
Thank you.
Yeah. All right, and let's just go through here. So what we can do, and just to sort of see how this kind of grows in complexity here, right? Because I can add 1 carbon, so now I have 1, 2, 3, 4. 1, 2, 3, 4, but now there are 2 different types of D 4-carbon sugars, right? So both of these are D. How do I know that they're both D?
The last asymmetric center has the alcohol group on the right.
Last asymmetric center, right? So we're only paying attention to this guy right here to determine whether it's D or L. And actually, it turns out in nature, like L sugars are not very common. All right, so nature has this sort of preference. We're going to see this with peptides as well, sort of handedness in what they choose to make. So then the only difference between our erythros and thyrose is the position, or the chirality rather, at carbon 2. Right, so notice that that's really what's going to distinguish these 2 4-carbon sugars is the chirality at carbon 2, or which side that OH group is on in our Fischer projection. So obviously you can see how this kind of grows out of control here pretty quickly, right? We now get 1 more carbon, We have all of these are going to be looking at this last asymmetric. These are still all D sugars. But now we have 4 different types because of those other 2 asymmetric centers, right? Again, the whole thing I'm just trying to impress upon you all, which side that OH group is on. That's really what's distinguishing all of our different sugars out there. And then we get to the 6 carbon sugars. And again, now you just have that other layer. So you got a total of 1, 2, 3, 4, 5, 6, 7, 8 different, all with that same D chirality. That same last carbon is still in that D conformation. Okay. Truth be told, nature really doesn't go bigger than that. We'll kind of see why that is in a second, but by far the most common are the 5 and 6 carbon sugars. That's what your body actually knows how to turn into energy. If it's making sugars, it might start out with this type of a building block, something smaller. But yeah, in terms of like what your body needs to process, in terms of like the sweetness that you get from fruits and stuff like that, that's all these 5 and 6 carbon sugars. All right, and in addition to, right, so we have we can tell whether they're D or L by looking at that last asymmetric center. We can classify them based on number of carbons. So again, this has 3, 4, 5, and 6. And then these were all aldoses. All right, and why were they aldoses? Because that carbonyl group is an aldehyde instead of a ketone. Okay. When we go to ketoses here, our simplest one, our 3 carbon, notice it doesn't have any sort of chiral indication. Why is that?
Because it's not chiral.
Because, yeah, you got no asymmetric centers, right? So I don't even know if it's really considered a sugar. I guess so, right? Because it has that CnH2ON formula. Nonetheless, really, when you get to 4, that's how when you have to start worrying about things, and you have that same level of complication. So these are all going to be D sugars. That alcohol group is again on the right, not the left, which would make them L. So then you get to number of carbons. So here's 4. We can grow it a little bit. This has still got that D stereochemistry, but now the position of the other asymmetric center has been flipped. Right, so that's your difference between ribulose and xylulose. Okay, and then again, last one, going to 6 carbons there, you have 4 different types. Okay, same idea, right? Position of that OH group, which again translates to the stereochemistry of the sugar. Okay, so now we're going to get into reactions here. Okay. First one that we're going to need to know, this is going to be an important one. Epimer Ization. Okay. We'll learn what epimers here in a second are, but I want to prove to you guys for a second that we actually already know what to expect in this particular reaction. Okay. This is, of course, a carbonyl group, right? So what do we call this carbon right here?
The alpha carbon.
The alpha carbon. Awesome. And what do we know about this hydrogen right here?
It's slightly more acidic.
It's relatively acidic, right? Absolutely. So exactly like what we've seen previously, that's what's going to happen here. We have this acidic alpha hydrogen. It's going to be removed by a base. Everybody take a second and draw me what I would get. This isn't quite complete yet. Something else has to happen here. See if you can't tell me what my intermediate should be. All right, so I'm missing an arrow here. My carbon, of course, can't have too many bonds, so that carbonyl bond has to jump up onto that oxygen. And I am left with an enolate ion. All right, so hopefully we can all rewind in our minds to chapter 17, maybe? Okay. Oh, I guess I'll leave this up. All right, and so then the next step is going to be, like we saw before, remember in these enolate ions, it's the double bond that can play the role of a nucleophile. So this is now going to go and grab a hydrogen off of a water molecule. Same time, this pair of electrons has to come down. And in doing so, you know, it's not necessarily apparent from the drawing here, but in this stereochemistry right here, these bonds are all 120 degrees, right? They're not your normal tetrahedral bonds. So the position of this hydroxyl group right here can effectively flip sides depending on which side that water approaches from, right? If the water approaches from the top, the OH group will be on one side. If it approaches from the bottom, it could be on the other side. The net effect is you're flipping that OH group. Originally, it's on the right. Final, it's on the left, or it's on the left and the right, right? So these are all dynamic equilibriums that can flip back and forth between the two in basic solution. Okay? So let's just pick this line apart right here. It can change configuration at the C2 for aldoses. First of all, in this example, am I looking at an aldose or a ketose?
Aldose.
So this is going to have this aldehyde group. So this is an aldose. So I am flipping the configuration at the C2 carbon, right? So that'd be, here's one, here's this guy here. Right, so these Epimer Izations are about flipping the stereochemistry at the C2 carbon for your aldoses, and the C3 carbon for ketoses. All right, so I'm gonna do some erasing and try to drive a point home here. Right, so then the big difference, if this was a ketose, this wouldn't be a hydrogen, but what would it be?
Well, I'm sorry, what was the question?
So the difference between an aldose and a ketose, right, is I'm going to take this hydrogen, I'm going to erase it. What do I have to replace it with to make it a ketose?
CH2OH.
Yeah, nice, right? So CH2OH, all the carbons have to be bound to an oxygen. So it's not a methyl group. It's a CH2OH, okay? And now it says that these epimerization reactions would also happen at the C3 of ketoses. Why not the C1?
Well, carbon already has 4 bonds, right? Like 4 separate bonds.
Well, this C1 is an alpha carbon. I can remove a hydrogen from C1 and form an enolate ion. But what's going to happen if I swap the position of this OH with a hydrogen there? Right? It's not an asymmetric center. So it's not that it won't undergo this same type of reactions, but you won't have any stereochemistry flip going on because it's not an asymmetric center. Right? So the only ones you really have to worry about if it's a ketose is that carbon 3. Okay? Let's just go back to our starting point here, right? So this is what an epimerization reaction does. It flips the stereochemistry at C2 for an aldose and C3 for a ketose. These guys right here, this pair would be called epimers.
And that's just a specific name for a kind of enantiomer, right?
it's actually a diastereomer, but whatever, right, enantiomers and exact mirror images, these only have one asymmetric center that's flipped, so it's a diastereomer, but yes, it's a specific type of diastereomer that's specific to sugars. All right, and then just to make sure we're all paying attention here, let's just get rid of all this business here. So if this is D-glucose, what happens if I take this and flip the bottom? That becomes what?
L-glucose.
L-glucose.
Boom, nice, awesome. L-glucose, right? So now we know the top carbon, if those are flipped, that's called something, that's an epimer, those are epimerizations. If it's the bottom carbon, that changes it from D to L, okay? All right. And notice that when your two epimers are considered different sugars, like one of them's glucose, one of them's mannose. Again, we're not going to bother memorizing names, but. Okay, so that's an epimerization. All right, reaction 1 we got to worry about. Reaction 2 is also going to take place in basic solution. It's going to be a little bit different than what we've seen before. All right, step 1 is still the same. Step 1 is still, you have this acidic alpha hydrogen, it's going to be removed. Boom, 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 and we get our enolate ion. All right, so step 1 in these enediol, this is what's called an enediol rearrangement, is going to be the same formation of the enolate ion. However, here we're going to see the enolate ion behaving differently than what we had seen before, okay? Here, the oxygen of our enolate ion is going to play the role of a nucleophile. Everything that we saw in chapter 17 was all about that double bond playing the role of the nucleophile. Here it's actually the oxygen that's playing the role of the nucleophile. Okay, so that's going to grab a hydrogen from water, and then, that's going to kick off an OH.
So, under basic conditions, would you get a mixture of products between reaction 1 and this one?
Yeah, and to be honest, right, like one of the things that's kind of weird, so you're like, what the heck? You throw this thing in a base, it's going to just give you a whole mess of different things. These are all reactions that can happen, but really inside of a cell, they would happen within the context of like an enzyme grabbing this sugar, and an enzyme could place that OH group exactly where it wanted it, right? So the cell has an ability to pick between which one of these things occur, but we're learning kind of like the reaction mechanism behind them. So just knowing that they do occur. Yeah, you don't really take sugar and throw it in basic solution and get all these mixtures of things. That would be a crapshoot, right? But these are the reaction mechanisms of how a cell turns, makes an epimer from one sugar to another, right? So the mechanism is what's really important here, not like us carrying this out in the lab. But yeah, that's a good question. All right. So then the next step here, so now we have what's called our enediol, right? So let's just pick this name apart real quick. En, of course, because we have what functional group?
A double bond.
The double bond, right? So that's that guy there. And then the diol, because we have an OH group on either side of that double bond. Okay, so the next step here is going to be a base comes along and removes the hydrogen from one of those two diols, one of those two functional groups. We get now another enolate ion, but here the charged oxygen, well, so let me actually back up for a second. We have another enolate ion, but let's just notice the difference between these two. In our first one, our charged oxygen was up at the top. Now we've essentially flipped where that charged oxygen is. It's on carbon 2 instead of carbon 1. All right, and then that can come down our double bond again, sort of what we'd expect acting as a nucleophile. Boom. So now what's the big difference between, can anybody spot what the big difference is between our starting product and our ending product?
One's an aldol and one's a ketol or whatever it is.
Yeah, ketose, yes.
Ketose, yeah.
Right, remember that ose ending is how we talk about sugars. Right, even if you noticed all the names of the sugars also end in ose, glucose, fructose, et cetera, et cetera. But yes, exactly. So this is how we change an aldose to a ketose and vice versa. All right, and Eric's right, both of these are catalyzed by basic conditions. All right, so we can either flip that first asymmetric carbon, flip the stereochemistry there, or we can change it from an aldose to a ketose or a ketose to an aldose. Again, we got a dynamic equilibrium here. All right, so this is the enediol rearrangement. This is important. Reaction number 2. Again, for our Epimer Ization, this kind of goes with what we've seen before, where we have our enolate ion and we have that double bond acting as a nucleophile. For these enediol rearrangements, it's something that we hadn't really seen before, where we have that charged oxygen acting as a nucleophile. Okay. Other reactions we've seen before. What's going to happen when I take a aldose and I toss in some sodium borohydride?
You get a primary alcohol.
Yep, so this will just reduce that first carbon to an alcohol. It's got a special name because it's a sugar, an alditol. And notice that we went from being mannose to mannitol. Mannitol is no longer a sugar per se. It no longer has that normal carbohydrate formula, but of course it's closely related, so the name's close. All right, and then if I had instead a ketose, notice I have the same number of carbons, and I reduce that, I could get 2 different products. What would be the difference between these two?
Well, you would get a secondary alcohol for one of them.
Yeah, and so that so if we just pay attention here, for our aldol, it is that top carbon that's being reduced. But here, it's the second carbon that's being reduced for the ketose rather. Does anybody see what my other product would be?
Would it be the L isomer?
Oh, yeah, okay, but the only thing is, right, we only differentiate D and L when we're talking about this bottom guy here. Right. But you're absolutely right. It's just a different stereoisomer, right? So this carbon right here is sp2 hybridized. So which stereochemistry you end up with is going to be a coin flip. It depends on which way it interacts with that sodium borohydride. Good news, a lot of unfortunate naming going on here, but nothing crazy that we've never seen before in terms of a reaction, right? We know that sodium borohydride reduces aldehydes and ketones to alcohols. Nothing crazy. We could even do the reaction mechanism if I was so cruel, right? Just to sort of remind everybody, if we were going to do a reaction mechanism, what do we always want to remember about these borohydrides, these hydrides in general?
A nucleophile.
Nucleophile, what's the nucleophile?
Hydrogen?
The hydrogen, awesome, right? So if we wanted to do the reaction mechanism, we'd have the hydrogen on this sodium borohydride coming, and it, well, I guess it wouldn't be that. It would be put this bond. Right, so remember all the way back to chapter 17, we got reaction mechanisms for this stuff too. And again, if you remember anything about these hydrides, they have nucleophilic hydrogens. All right, so that is reduction. We can also do oxidation. So there's going to be a few different oxidation reactions that we learn about. First one is going to be oxidation via bromine. Okay, bromine can oxidize an aldehyde. What would we get if we oxidize an aldehyde group?
Carboxylic.
Alcohol?
Boom, carboxylic acid. No, alcohol is reduction.
Yeah, that's
We
reduction.
oxidize, it would be carboxylic acid. Okay, so bromine can convert aldehyde groups to carboxylic acids. This is actually, bromine is actually used as a test to see whether or not you have an aldehyde or a ketone, because it cannot oxidize ketone groups. Br2 is red, and if it oxidizes your sugar, you get this colorless bromide ion. So this is what would be called a bromine test. It actually works for all aldehydes versus ketones. But if you know your compound has a carbonyl group, you can use bromine to tell whether or not it's an aldehyde or a ketone. Okay, so same thing, right? I mean, I think the hardest part of this chapter is we have these big, ugly molecules here, and really we're just pulling on chemistry that we've already learned about, right? So this is just chemistry of the aldehydes versus ketone groups. All right, and so again, this is specifically going to be for aldehydes and not ketones, Br2. If you had a ketose and you put in some bromine, it would remain red. There wouldn't be any sort of a reaction that occurs. All right, so this is one way we can test whether our sugar is an aldose or a ketose. All right, this next one here is going to be what's called Holland's reagent, and this is going to oxidize both aldoses and ketoses. So if you were hell-bent on oxidizing, no matter what it was, you would use Holland's reagent. And the first step with Holland's reagent is going to be to treat it with a base, and what do we already learn our base can do? Can switch the stereochemistry at, in this case, C3, but it can also convert my ketose to
Aldehyde?
yeah, to an aldose, right? So the other thing that it can do, is convert that ketose to an aldose, right? So that's really the first step in this Holland's type reaction mixture. And then you actually use silver instead of bromine. Really, you just have it all in one reaction mixture. The first step being to convert to an aldose, and then you get oxidation as normal. All right, but Holland's you would use if you wanted to convert either an aldose or a ketose to a carboxylic acid. All right, we got one more oxidizing agent to talk about here, and this is nitric acid and heat. So nitric acid is the strongest oxidizer that we're going to talk about here. And it can oxidize not only the carbonyl group at the top, whether it's an aldehyde or a ketone, but also, well, it's just the aldehyde, but also the bottom one here. Right? It can also oxidize an alcohol group to a carboxylic acid. So here we would get a dicarboxylic acid.
Does it oxidizes ketoses as well?
Well, it would oxidize the bottom half, but it wouldn't be able to oxidize the actual carbonyl group itself. So it would oxidize a ketone because it has that last OH group on there, that terminal alcohol group that can be converted, but you wouldn't get the dicarboxylic acid.
Gotcha. Okay.
Right, and this is, again, now we're thinking like our harshest possible oxidation method. We got this strong acid as well as heat here. All right, so reduction, kind of nothing special, just our sodium borohydride, same reduction of aldehydes and ketones that we saw before. For oxidation, we got 3 different methods. The one I think maybe put in a special place in your mind is the using bromine to oxidize, because that's actually a way that we can very easily tell whether we have an aldose or a ketose. All right. Let's go through, let's walk through this.
The last reaction,
yeah,
with the strong base, is that for both aldose and ketose?
For strong base, you mean this guy right here?
Yeah.
So this is a, nitric acid, strong acid. If it has, so let's do this. An aldose, you would get a dicarboxylic acid product, right? It would convert both that aldehyde group and that terminal OH group to a carboxylic acid. If you had a ketose, you would only, it wouldn't be a dicarboxylic acid, you would only get one, because it would oxidize that terminal OH group, but it wouldn't be able to oxidize the carbonyl carbon.
Okay. All right, thank you.
Okay. Again, so now this is the Kilian Fischer synthesis. Before we who cares who they are? This is actually using stuff that we already know based on previous chapters, right? So when you see this guy right here, what are you thinking?
It's a strong nucleophile.
It's a nucleophile, absolutely. Not like the crazy Grignard type, but yeah, it's a good freaking nucleophile, right? And so what is that going to do with our sugar?
Will it remove the alpha hydrogen?
Oh
wait, no, never mind.
That's not a bad guess. But no, it's actually, that's what's part of what makes it a good nucleophile, is that it's a good nucleophile, but not a great base.
Yeah, not a great base, yeah.
So
as soon as I said it, I was like, wait, that's not right.
It's a weird category, right? Because usually our good nucleophiles are good bases. This is one of those sort of exceptions. But if we had our nucleophile here, do we have an electrophile on our sugar?
Yeah, the aldehyde.
I swear, if I hadn't beaten this over y'all's head, electrophilic carbonyl carbon, right? Absolutely. So everybody take a second and see if you can't draw me what I'm going to get here.
These things take a minute to draw.
Yeah, well, you don't have to draw the whole sugar. This part down here isn't actually going to change. But yeah, I think that's the hardest part of the chapter, is just looking at these big, ugly molecules. Right, but after this first nucleophilic attack of an electrophilic carbonyl carbon, we have that world famous
Tetrahedral
intermediate, right? And then do we have a good leaving group?
No.
No, so the only thing we can do is follow that up with acid and get an alcohol group, right? So just to keep track of who's who here, this carbon right here is now this carbon. But of course I can't control which side my nucleophile is going to attack from, so we actually have two different stereoisomers that are generated. Notice that the only difference here is which side that OH group is on. All right, so then what happens after that is you're going to follow this up with H2 and palladium. What does that usually do for us?
Reduces.
So that's going to be reducing, and in this case, we're going to reduce specifically this nitrile group for whatever reason. I have no idea why. Barium sulfate is also in this mixture, I think to make it a weaker reducing agent. And so that will actually reduce not fully to an amine. Anybody remember what we call these?
An amine?
An
Yeah,
imine.
nice. So this would be to an imine. Okay. And then we can treat that with acid and water and replace that imine with a carbonyl group. All right, and again, the big difference between these sugars is the position of the OH group on carbon 2. So they are what? What special name did we have for two sugars that only differ in their stereochemistry at carbon 2?
Epimer.
Epimers, absolutely. So here we have, again, they just differ at carbon 2, so they are epimers. And let's just take a note of what really just happened here. We had a 1, 2, 3, 4 carbon sugar, and at the end we now have a 1, 2, 3, 4, 5 carbon sugar. All right, so this is a way, this Kilian Fischer synthesis is a way to grow your sugar by exactly 1 carbon. Again, the only sort of catch is you get 2 different epimers out of it.
Could you do the same thing like with like an alkyl halide? Like add carbon chains?
An alkyl halide.
Like in the last chapter, you could add carbons onto benzene through with alkyl halides. It might be a stupid question.
No, I get what you're saying. No, so the thing about the alkyl halide that you were kind of the thing about the alkyl halide was it was playing the role that our sugar is currently playing, right? It had that electrophilic carbon. So in this case, you couldn't have like a sugar and an alkyl halide together and not have that do anything for you. All right, but again, the whole shtick of the Kilian Fischer is we went from an aldopentose to an aldohexose. Actually, in this case, we went from an aldotetraose to an aldopentose, but whatever. Bottom line is you can grow by 1 carbon. I think that this is specific to the fact that pentoses and hexoses are by far the most common. All right. All right, so that is lengthening the chain, right? So the next one we're going to talk about is how we shorten the chain by exactly 1 carbon, right? So this is now going the other way, going from an aldohexose to a pentose. And this is the wall degradation. All right. What happens when you have an amine and a carbonyl group with trace acid?
You will get an amine.
Yes, this is again, now we're going to go through this imine step. This is a little bit weird that we saw before because there's an OH group on there. We're used to seeing some other carbon-containing compound, right? But nonetheless, I trust these guys know what they're doing. Okay, so we get our imine, and then we're going to mix in acetic anhydride. Not a big deal if you guys don't remember the name, but this is what acetic anhydride is. Remember, it has that anhydride group. Okay. So now we've done the exact reverse, and instead of reducing, we have now oxidized an imine to a cyano or a nitrile. Notice that that puts these acetate groups on every single one of those hydrogens. This guy reacts with the alcohols as well. All right. If we treat it with, basic solution, we would get, that's how you're going to remove all those acetate groups. Basically, you're replacing all those ACs are now being replaced with hydrogens. Awesome. All right, the last thing we'll do is also remove that nitrile group. Why is that? How did I get rid of a carbon in here? All right, so it's literally the exact kind of reverse of what we saw before. In the previous one, our nitrile group was acting, or our cyano group was acting as a nucleophile. Here, it's acting as a leaving group, right? So you have your hydroxide coming and attacking this carbon here. That kicks off that cyano group as a leaving group. We're left then just going to be lazy here and put R. And remember that these, does anybody remember what we called them when they had two OH groups on the same carbon?
A gem diol.
Yeah, so then our gem diols, remember, are in equilibrium with our aldehydes, right? So this is kind of the reverse first. You have your hydroxide group acting as a nucleophile, kicking off that nitrile. That's how we got rid of a carbon, right? That gives you a gem diol, which is in equilibrium in a way that very greatly favors your aldehyde.
Are nitrile groups good leaving groups?
Yeah, they can be living groups for sure. I mean, you're going to want to have a larger concentration of, your hydroxide than you are of sugar or something like that. You're going to want to use a little Le Chatelier's to help you out. But yeah, they can be leaving groups. This guy is relatively stable by itself. You're then playing like a Le Chatelier's kind of group there, principle there. Making sure you have much more OH in solution, or again, realistically, these happen in a cell where that cell sticks this OH group directly next to that carbon, so that attack is like really favorable. Proteins are pretty sweet. We'll talk about those next time, but they're basically ways of like forcing two reactants together such that they react with one another in a very specific way, not in solution where you're relying on random collisions to get things to happen. All right, so those are our, 6-ish reactions that are pretty important here thus far, things that we can do with our straight chain sugar. The last one that we're gonna end on here is probably the most important one, at least in my opinion. And this is going to be an intramolecular reaction, okay? Again, we know our carbonyl carbon likes to play the role of electrophile. In this molecule, the rest of this molecule here, do I have any nucleophiles? They're not
Well,
great nucleophiles. Any weak nucleophiles?
well, the alcohol group could act as one.
Absolutely, right? So this is this last reaction here. This is going to be a cyclization reaction, and it's going to involve the alcohol group on the sugar, specifically that the last one, or the one, how do I say this? The one at the last asymmetric center. Okay, everybody take a second and, given what I just said about how this green carbonyl carbon is the electrophile and how this, well, not red, because we already got a red one. This purple alcohol group is going to be our nucleophile. See if you can't tell me what reaction we have here. All right, so this is going to go attack the carbonyl carbon. Oxygen can't have, carbon can't have more than 4 bonds, so that's got to move that pair of electrons up. And then the last step is going to be a proton transfer of this hydrogen over to this oxygen, right? You got to then transfer that proton. And what you get, so let's first, really this thing would have to kink itself into a loop here. All right, so this is just what I showed, but a little bit more like anatomically correct, or anatomical is not the right word, but you know what I mean. Now we have our hydroxyl group playing the role of a nucleophile, attacking that carbonyl carbon that jumps up. And then again, the last step, which isn't actually shown on this slide, but let's make sure we all understand why that would be, is that this hydrogen has to jump from that oxygen over to this one. Right, so there's going to be a proton transfer step. If we want to see, I guess, let me just do this more explicitly. Don't worry about the color coding for right now. I'll explain what that means more in a second. But here, whoops, so what I would have, right, so ignoring all these various R groups here that I'm kind of not paying attention to right now, you would have a protonated oxygen that is now a part of the ring, right? So notice that these closed rings have oxygen as one of those members of the ring. And so the last step would have to be this guy reaches over and grabs that, and this pair of electrons comes down, which I didn't explicitly draw. All right, so these are these intramolecular reactions that take place. And you can have 2 different possible products depending on the stereochemistry of what was formerly your carbonyl oxygen. All right, so this is a busy slide, so let's go through this real quick. Get rid of all my. All right, so first of all, let's just focus on one of these closed rings for a second here. 9 times out of 10, when you actually look in like a biochemistry textbook, you don't see those Fischer projections of the sugars. You actually see them in closed chains like this. Okay, that's because that's how they exist in the cell. If we want to look, these are a dynamic equilibrium that takes place between the straight chain and both of these closed rings. But at any given time, only about 0.2% of the molecules are in that straight chain form. The vast majority is in one of these two closed ring forms, right? So in your cell, the sugars that are floating around are actually in rings, not in straight chains. As chemists, when we're writing them down on paper, it's very, very helpful to look at them in their straight chain form. But nonetheless, in the cell, this is how they're going to be floating around, okay? So now I said you had 2 different possible products. Let's take a look at what the difference is here. All right, so the alpha form is going to have to do, is because the OH group on what's called the anomeric carbon is pointed down. The beta form is because the OH group on what's called, again, the anomeric carbon is pointed up. Okay, everybody take a second and looking at your Fischer projection, this guy here, see if you can identify what the hell that anomeric carbon is. What am I talking about?
Is it the aldehyde carbon?
Yeah, your carbonyl carbon. What was your carbonyl carbon in your straight chain form is your anomeric carbon in your closed chain form. Okay? Another fun vocab words that we got to learn. You know, unfortunately, when we're talking about sugars and when we talk about peptides, you've got language that was constructed by biologists, not chemists. So they just got different names for stuff than we have been used to. Okay? Again, your anomeric carbon, I'll be better about coloring this. Let's make this guy pink. Here is your anomeric carbon. And that was originally formerly known as that carbonyl carbon. Okay, and that's why we get these 2 different products, the alpha and the beta, is because I can't control the stereochemistry of where that oxygen's going to go. It's either going to be pointed down, which we call the alpha, or it's going to be pointed up, which we call the beta. Okay, so first of all, I know, again, this slide is really, really busy. We're going to have to take a little bit of time to pick apart what's exactly going on here. Most important takeaway that I need you guys to understand at this point is 1, ring closure. We're talking about an intramolecular reaction. It's always going to be the hydroxyl group that's on that last asymmetric carbon. It's never this last one here. It's never the very terminal one. To be honest, I don't know why that is. I just realized that. I'll look that up. That sounds interesting. But it's always going to be the one on the last asymmetric carbon. Okay? And then right, important ring closure is intramolecular reaction. And then you get 2 possible rings out of that. One we call alpha, that has to do with the fact that the OH group's pointed down. The other one's beta, the OH group is pointed up. And these are in a dynamic equilibrium with one another, right? One of the weird things about equilibrium is when we talk about these percentages, it's not like that's frozen in time. You have alpha rings converting to straight chains, converting to beta rings, and back and forth and back and forth and back and forth. This is all sort of a dynamic process. But if you were to be able to freeze time at any one given moment, vast majority of those sugars are in that closed form. Okay? One more thing to leave you guys, we're sort of out of time here, but one more thing I want to leave you guys off with, just to sort of explain the slide a little bit better, is that these are kind of closed chain ways, are a very specific way to draw your sugars called Hawthorne Projections. So I'm going to get rid of all the crap that's decorating the outside here so we can sort of focus on just the shell of it. All right, but this would be like a Hawthorne type projection of your sugar. It's not quite our normal chair conformation that we're used to seeing. You have the oxygen in the back, and then the other carbons are sort of sticking out in front. And the whole reason that we have these types of drawings is because you can draw all the possible different sugars using this type of projection, right? Because the only thing that differs between sugar molecules is, one, the length of the chain. But if I'm talking about a 6-carbon sugar like I am here, I can draw all the different ones. Oh man, I can draw all the different ones by just, you know, flipping this OH group from down there to up here, right? Which way those are pointing, either up or down, that's what differentiates between all your different sugars, okay? So this Hawthorne projection is a specific way of drawing sugars. There's an easy way to go from your Fischer projection to your Hawthorne projection. All OH groups on the left will be on top. All OH groups on the right will be pointed down. But we're going to pick up with that next time, all right? I just kind of wanted to explain all the busyness of this slide real quick. And these Hawthorne projections are going to be something that we need to sort of look at and be able to go from Fischer to Hawthorne and Hawthorne to Fischer. All right, but we'll start, pick up next time with practicing that. Anybody got any questions about the reactions specifically that we've gone over up till now?
If there's if one of these hemiacetal reactions, like the intermolecular ones, occur, how do any of the other reactions apply? Because those were all towards straight chain sugars. Yeah,
right. And because, again, remember, this is a dynamic equilibrium. So even though it's only in this form, this straight chain form, 0.02% of the time, if I throw this sugar into basic solution, that 0.02% will react. And it'll be, you know, taken out of the pot, right? So it's just important to remember that even though these numbers, you know, are what they do say something. They're really a picture of like a freeze in time. You're always jumping back and forth between these guys. Cool? All right. Yeah, so I am going to get, my goal is going to get to, your exams will be to you on, you know, by tomorrow, and then Thursday I'll sign on an hour early so you guys can ask any questions if you have them about, about your grade or problems, you want to see answer keys, all that good stuff. One more thing that I will say, and I'll actually put this in the email too so that everybody knows. Because of the circumstances of this pandemic, the withdrawal date for the course has been extended all the way until May 15th, so next Friday. And not only has the withdrawal date been extended, but you would, instead of getting a W on your transcript, you'd actually get what's called an excused withdrawal or an EW. And it doesn't have the same weight as a W. It doesn't count towards the number of attempts you've made for a course and blah, 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 blah. So bottom line is when you do get your exam grade, you want to take a look at your overall course grade, make sure you're on track to pass. And if not, you want to take advantage of that extended withdrawal date because it's not going to hurt your transcript like it normally would. All right. So in addition to that, and I'll make sure that Canvas is all updated with your grade information. The only thing it's not going to have is those participation points. That I can't do until, you know, we've had all of our class periods. Cool? All right. All right, y'all. Then I will see you on Thursday. All right. And we'll pick up with all this sugar business.
I have one more quick question about the lab notebook.
Yeah.
I can't remember. Does the lab notebook require the calculations, or is that just on the report? It's fine on the report. Okay. Normally I would make you do it on the notebook just to force you to do it twice, but I don't, once in class before you leave and then once on your report, but I don't have that. It's not to do the same thing. You'll just do them back to back, and that's stupid. So yeah, I mean, before I just did it so you'd be forced to practice, but I can't really do that here. Okay, cool.
Cool. All right, y'all. All right, I'll see you next Thursday. Not next Thursday, but Thursday.